All right, I think we can get started here. My name is Amal Khatak. I'm the director for the Mid-America Transportation Center. Today with us is Dr. Haitao Lee, who's a professor and chair of the Supply Chain and Analytics Department and founding director of the Laboratory for Advanced Supply Chain Analytics at the University of Missouri, St. Louis. He also serves as the associate editor of the Journal of Operational Research Society and Transportation Journal, and serves on the editorial board of the International Journal of Project Management. Today, he's going to talk about optimizing the configuration of food supply chains. So without further ado, I ask Dr. Lee to make his presentation, and we will hold our questions till the end of the presentation, and there will be a time for question and answers. Thank you very much.
Thank you, Professor Khatak, for the invitation and introduction. Hi, good morning, everyone. It is my pleasure to share with you my research on optimizing food supply chain configuration. Let me get started with some background introduction of our institute. University of Missouri System St. Louis campus is located in the greater St. Louis metropolitan area. And our department, Supply Chain and Analytics Department, hosts the only PhD program in supply chain analytics in this region. And we're very proud our recently launched new Master of Science in Supply Chain Analytics program was ranked #1 by Intelligent.com in 2022. We are very pleased we're able to connect well with the local business through our industry advisory board. So here I list the current board members. As you can see, you see some bigger companies in the region, such as Bayer, AB InBev, Boeing. It also includes some other medium-sized companies, as well as some non-for-profit organizations, such as the St. Louis Regional Freightway and St. Louis Food Bank. All right, a little bit information about my last research lab. So this is a recently launched research lab. We focus on research on developing and applying data-driven analytics and AI to address various supply chain related challenges and often opportunities. So here I list a few ongoing efforts we are pursuing right now. So some of the topics are relevant to what we're going to talk about today. For example, the climate smart food and agriculture supply chain design. That's also related to the bigger challenge of how we manage supply chain under pandemic. That certainly has to do, many other sectors and industries as well. I also want to mention the one I listed at the bottom, on the study of how can we better utilize our nation's inland waterway system, especially the use of Mississippi River, not only because of its national impact and strategic importance to our country. This is also a topic that's very relevant to the place where we are, right? In this greater St. Louis region, we are in a unique geographic location with, multimodal transportation infrastructure in place. So this is a research topic we've been, pursuing over the years and will be, in the near future as well. So let me give you everybody a overview of my presentation today. I will start with an overview of the food and agribusiness supply chain. We'll highlight about its unique characteristics and complexity and challenges. Okay, yeah, from my understanding and my experience. And then we'll introduce the so-called food supply chain configuration problem, which will be our main focus today. Okay, I will introduce the problem with some background, motivation to address this problem in the context of general supply chain management, and then dig into its optimization model formulation. I'll certainly present the case study we did and have some discussion on the findings and results. All right. So agribusiness supply chain is certainly a complex system. It is often very complex because it has so many players. Okay, let's start with the input sector, right? These are the producers, manufacturers that provides the seeds, chemicals, fertilizers, to the industry. And then, of course, we have producers, right? Farmers, growers, okay, yeah, that actually do the planting, harvesting, and really the production part of the food chain. And then, of course, for most of the food items, we'll be looking at this processing sector, right? Yeah, so doing value-added processing to produce the food products, to the market. And of course, on the market side, we have wholesalers, retailers, and of course, throughout the entire supply chain, we'll rely a lot on transportation and logistic providers. Okay, but that's not all, because often, sometimes government, right? Government agencies, non-for-profit organizations also play a role in this supply chain. For example, we can think of a food bank, right? Food bank, typical food bank actually has a very unique positioning in the food supply chain because it usually has a very good visibility. Okay, yeah, it actually touches almost the entire supply chain, from the procurement, purchasing stage, and then they distribute, right, to those in needs. And I'd also like to highlight the importance of what I put here on exogenous factors. Okay, so what do I mean by that? Well, we'll be thinking about a number of factors that's beyond, right, the decision makers' control. For example, a number of environmental impacts factors, such as the weather, the temperature, rainfall, right, and the availability of natural resources, like for example the use of land, right, the availability of water, and a lot of these fall under the bigger umbrella and a very timely topic that many people are concerning right now, that has to do with the bigger picture of climate change, right, and the issue of sustainability. Yeah, so given such a complex system, there are certainly lots of challenges, but my perspective is always many of these challenges we're looking at right now can often be opportunities, okay, if we can properly address them. So I have another slides showing the some unique characteristics and issues that we need to address when we try to optimize a agribusiness supply chain system. So perishability is certainly a very unique one, right? This feature almost does not exist in typical manufacturing supply chain, right? When we talk about computers, other commodities, but this is extremely important when we look at food and agriculture supply chain, because especially when we look at products such as fresh produce, fresh fruits, right, and the poultry supply chain, meat, and so forth. Yeah, so definitely want to capture that. Seasonality, right? Again, this is unique and important. Seasonality impact not only the demand, right? We probably first think of demand, but certainly supply, okay? I think mostly supply, because many of these products have their growing season, right? If we are talking about crops, different crops typically has a growing season, and that will directly impact the supply. Sometimes it will have impact on the demand, okay? And in conjunction with that is, of course, the price, okay? Yeah, so seasonality, very important, unique feature to address. Scalability, that has to do with the size, right? Often a real world food supply chain involves many players, like we showed earlier, okay? So sometimes we need to be able to handle a problem, a decision problem at the larger scale, right? With probably a large size optimization model, where we need to find efficient and effective solutions. All right, yeah, so scalability, complexity, we already touched that. And uncertainty, yeah, I put it on top. This is a significant challenge, okay? Yeah, so think about the world we're living right now, right? Think about what happened in the past 2 years because of COVID, right? And more recently, the conflict in Ukraine that, have significant impacts to the world food supply chain and supply. So the existence and impact of uncertainty gonna be there, gonna continue being there, and that creates a big challenge for us in terms of how can we address some of these decision needs, okay, yeah, in the agribusiness supply chain from the strategic, tactical, and operational level, while considering the impact of uncertainty, right? That leads into a very important metric I'm going to talk about next, related to the idea and the needs for resilience, right? The idea of resilience. I think that's a very high-level theme and topic for us to think about, right? How can we design the supply chain such that it is not only efficient in the short run, but has this intrinsic resilience, right? That is able to, cope with risks and uncertainty. All right, there we go. So, so here I highlight some of the performance metrics, okay? Yeah, from my perspective, I think along the way, we are at the time that we really need to address these multiple supply chain metrics, okay? Or about the food system simultaneously, okay? Yeah, let me start with efficiency. This is perhaps the classical, mostly addressed performance, right? For example, in the so-called precision agriculture field, right? People focus a lot on, improve the yield, right? At the production stage, okay? By really precisely determining, what to grow, when to grow, how much to grow, and in which part of the field, right? By through the so-called precision agriculture approach. That has been there for a long time. Then, of course, if we extend that to the entire food supply chain perspective, there are lots of emphasis in the past on, the efficiency of the food supply and distribution system, right? Down to the operational level in terms of food delivery, last mile delivery. So efficiency is something we are already very, very well familiar with, okay? And relatively well-studied metric, I would say. Safety comes up next in my list because of its importance for the food system. And in conjunction with safety, we could also be addressing the metric of quality. I think safety and quality are actually intertwined with each other, right? On one hand, in recent years, we've seen lots of challenges coming out of food contamination, right? For example, the salmonella contamination in the poultry industry that pose significant threats and negative impacts to our society and consumers. So how can we design and operate a food supply chain well, to ensure our food is safe and with sufficient level of quality, right? Yeah, in terms of nutrition. Resilience, okay, we touched that earlier. again, very important. Okay, so at very high level, we could be, addressing the uncertainties and risks on both the supply side as well as the demand side. Okay, yeah, at very high level. On the supply side, again, we could be continue addressing the impact of climate change. Okay, I think this issue, is becoming more and more prominent. Okay, we're seeing this happening everywhere and becoming more frequent, right? Those extreme weathers, okay, we're seeing here that's happening in our country, okay, in California, right? Extremely high weathers, making, it's very challenging for food, for agriculture, for farmers to handle the lack of water, right? And these challenges are especially perhaps more prominent, more critical in some less developed countries, such as many of the African countries. I just came back, just paid a visit to South Africa this past summer, okay, yeah, to fulfill one of my funded research projects on addressing the agribusiness supply chain design under climate change. I paid a couple of visits to the local farms in the Cape Town area, and I got to know their significant change needs. They really need help to come up with a sustainable business and supply chain plan so that they can be sustainable, right? Both economically and and environmentally moving forward. Yeah, lots of challenges there, and we're happy, very pleased we're able to offer help. Okay, equity. Yeah, so another important topic, right? How do we serve especially those underrepresented, disadvantaged population groups, right? So here I give you an example again, the role of food bank, right? So they serve that unique role, and in the U.S. we're very pleased to see we actually have a very well-established food bank system, right? At different levels, right? At the state level and regional level. But there are still lots of challenges for them to be able to operate efficiently, right? Yeah, and to better serve their mission. And another story I want to share related to equity is my observations, my takeaways from my farm visits in Cape Town, South Africa. So it was really interesting and striking for me to see that both the two farms I visited actually started with their primary mission to serve the disadvantaged group. Okay, yeah. So both farms have a clear mission to provide employment opportunities for the disabilities, right? So one of them is more in a more urban setting. Okay, so they use their farm gardens, to hire disabilities, to provide that employment opportunity. The other farm, which has a much larger scale and much bigger size, they have a clear mission to serve the women, in the vicinity villages who have been experiencing significant social issues and family issues. So they actually established the farm to provide employment opportunity for women. They also actually established their training educational center for the kids, okay, to provide a place for their employees' kids to stay while their moms work at the farm. So it was quite interesting to see that. Okay, yeah. So this equity metric become relevant, and then of course sustainability in terms of environment, economic and social perspective. This is going to continue being important. Yes. So here we're seeing a big challenge for us, right? For the farmers, every players in the food system, to think about how to achieve these, right? Simultaneously. That's almost not possible because, as you can see, many of these metrics can be conflicting with each other, right? So for us, researchers dedicated in data data-driven decision support, right, and use of analytics, our big theme is how do we design, right? How do we come up with innovative data-driven decision support, right, to best trade off, right? Let's say, yeah, that's something we can always do, right? Can we best trade off these multiple dimensions of performance metrics? So I think with that goal, we often need interdisciplinary research teams, right? Yeah, you can see these type of research often require collaboration between, crop scientists, okay, people in ag economics, as well as in supply chain and analytics. Yeah. And also the importance of engaging with industry collaborators and stakeholders. Okay, also very, very important. All right. Let me give you the scope of methodologies. Okay, yeah. So of my approach. So I'm heavily into the use of different analytics or AI if you want to. Okay, that's fine. But no matter what terminology we call these methods, right? I always like this approach. Okay, to present or classify these different methods from the user's perspective, right? The purpose, okay? What purpose do they serve? Okay, we can classify these methodology into descriptive, predictive, and prescriptive, okay, analytics, yeah. By descriptive, we're talking about the use of classical descriptive statistic and visualization techniques to describe what happened in the past, okay? Often we want to go a step further, right? That's where we can use, again, statistics, econometrics, or nowadays, some newer machine learning techniques or simulation to predict, right, what's going to happen in the future. Yeah. My research focuses a lot actually on the third component, that's called prescriptive analytics, or the use of optimization to prescribe, right, what to do and how to react. Okay. So you will see, the talk I'm giving today, okay, I'm presenting today, focus on the third component, okay, that is optimization modeling, okay? Yeah, that's my main research methodology. The paper has been published in International Journal Production Research 2020. So I'll be happy to share the reference, okay, if you are interested. So here we coined, okay, we presented this new problem called supply chain, food supply chain configuration problem to address the tactical level, okay? The tactical level decision concerning mode selection and the so-called inventory positioning, okay, throughout the food system, okay? Yeah, so the note on tactical level is important because here we do not address the strategic level of supply chain network design. Okay, yeah, we're assuming the physical design structure of the network is given, but we address the mode selection and safety stock placement decisions. Okay, yeah, we try to capture the complexity of a food system. Okay, in terms of the demand and time dependencies of different stages of the food chain, okay? We certainly address the perishability feature, okay? And the modeling framework captures the loss of food during the supply chain system, yeah. And the model addressed multiple performance metrics, as we highlighted earlier, if not all of them, okay? Yeah, and particularly we address cost, lead time, right? And food quality, yeah. All right, let me give you a little bit background, okay, about this supply chain configuration problem in general, okay? So let me start with the so-called push system, right? We know that the push system is the classical system where we emphasize a lot on productivity, efficiency, right? When you produce as much as you can, at each stage, that leads to potentially, lots of working process inventory, okay, represented by the triangles, okay, those represent the WIP in between. So that's the downside of a push system. And then we have this idea of pull system, right, or in conjunction with the idea of JIT or just in time, where we only produce, right, when there is a demand from the downward, right? So the pull system really has the advantage of reduce the working process inventory. You see that advantages, but on the other hand, pull system often, has a potential disadvantage where, it's hard to achieve the large scale, right? Or the large volume, okay? It often fits for, the production system where you have lots of a variety, right, for the end products. So this is why in real world, often there is this incentive to integrate the two, right? So through the so-called push and pull boundary, this is perhaps, really the mechanism behind many of the real world supply chain we are looking at, in different industries now, right? You see here I'm illustrating, in this approach, we have the forward part of the supply chain driven by a pull system, right? That's driven by demand, okay? Whereas the upper part of the supply chain driven by forecast, it's a traditional push system, okay? So this type of integrated system has well-known advantages, okay? Let me give you some well-known example. For example, Dell's PC supply chain, right? Where, at the end of the supply chain, Dell allow customers to configure, right? You see, configure what they need, okay? Yeah, the type of configuration they need. That's the idea of pull system or driven by demand, right? But Dell also maintain lots of modules, parts, components, right? Because they don't want to start from scratch, okay? So they maintain those semi-assembly and parts, more like a pull system to achieve both flexibility as well as the scale, the volume they need, okay? Yeah, so there are many other examples. But then the question becomes, what should the push and pull boundary be, right? In real world practice, how do we optimize that? And we know that's an important decision because this is an underlying mechanism of the real world supply chain, okay, we're looking at, right? So we may have a make to stock supply chain, right? Where you have the push pull boundary pretty much at the last stage for finished goods, right? That's where we call it make to stock. And then when you push the boundary backward, right, you have assembly to stock, right, or assembly to order, right? You push back forward, you have the make to order, right? You keep fewer and fewer, inventory or safety stock for your parts and components. The other extreme is the engineering to order. That means even the design of the product needs to be customized. Okay, yeah. So for us, our interest is to optimize this, push-pull boundary, okay, for a supply chain, in particularly for a food supply chain. All right. So of course, in our setting, we do want to capture the unique feature of food loss, okay, especially when we talk about perishable food. So this is where we introduce a loss rate, okay, delta, okay, yeah, very general, delta captures the loss of volume, okay, see, that's important, okay, so here we are capturing volume. But we know that food loss and waste also means quality, right? So in our modeling framework, we actually also design this mechanism to capture the quality, which has directly impact on the food price, right? Ultimate price in the market, as well as, the nutrition, they can provide, okay? So we do have this linear and nonlinear function in place to capture the deterioration of quality, okay, of food items through the supply chain. Yeah, I don't want to get into too much detail, okay, because of the time limit. Yeah, but that these two features are, certainly considered. Okay, so this is an illustration of the quality function we use in our modeling framework. Okay, yeah, so you can see, we could either use a linear, okay, quality function that goes down, capture the decrease of quality, in terms of as a function of shelf time, right? Or we could consider a nonlinear function, okay, yeah, captured by this exponential function, okay, represented as the blue curve. Yeah. All right. And then we need a mechanism to capture the system-wide quality, right? So here we consider these different substructure that could exist in the general food supply chain, okay? Yeah, so on the left is the parallel supply chain. In the parallel supply chain, the quality level of this parallel structure gonna be the minimum of the three, right? All we need is take the minimum, okay? If the structure is serial, right, they are dependent, right? That needs to be, the multiplication of the quality score, right? Because each stage is dependent. And then when you combine the two, we're gonna have a mixture of, multiplication and the minimum function in our model. So the model is highly nonlinear, because of these, unique structure characteristics we want to capture, okay? So we conducted a case study of a grape supply chain, okay? Yeah, in our paper, yeah. So we just pick one particular use case, okay, to focus on grape supply chain where we, present this very generic grape supply chain. I don't think that this captures much of the complexity we see in reality, okay? Yeah, it's more like a use case where we demonstrate what the model can provide, okay? Yeah, so we consider the fresh grape as inputs, okay? Yeah, different outputs at the end of the supply chain in terms of reasons, okay? Fresh table grapes and wine, okay? Yeah, so you can see we also consider different parts, components needed, like boxes, packaging, needs, oak cask, okay, used for, producing wine. Again, this is a simplified version, okay? But nevertheless, it provides a starting point for us to, to play around, to analyze what the model, how the model works, okay? Yeah, what the model can provide. So I also provides a slide on the use case data, okay? This will give you a better understanding on what's the model going to take as inputs, right? So basically, we consider every node in the food supply chain described by the so-called bill of materials, okay? I hope some of you are familiar with that terminology. So bill of material describe the product structure, right? Every raw materials, ingredients, parts, components needed for the end products, okay? And for each node, right, we also consider, very importantly, different options, okay, different modes that will have trade-off in time, in cost, as well as their loss rate, okay, their shelf time. Yeah, this is really the key. For example, when we talk about picking for the raw fresh grapes, right, we can use manual picking method versus machine, right? So they're gonna differ in their cost and lead time and the quality. Okay, so that just give you an idea on what kind of data we'll need. Okay, I will go through the formulation very quickly. Again, if you are interested, feel free to get our paper, published paper, and I will be happy to give you more details. Let me directly jump into the decision variables, okay, of the model. So a very important key decision the model tries to optimize is the so-called mode selection, okay? In other words, for each stage in the food supply chain, we'll address the configuration decision in terms of which mode to select, right? For example, manual picking versus machine picking, right? When we talk about packaging, it will have different packaging options, right? Yeah, some higher quality packaging options will be more expensive, but it will have better quality in terms of reducing food loss, right? We could be addressing different transportation modes, right? Shall we ship by air or truck, right? Or train? Apparently these vary and often have trade-off in their lead time, cost, and quality, okay? Yeah. So another important decision the model optimizes is the so-called outbound and inbound service time, okay? These two decision variables directly captures the amount of safety stock, okay? Yeah, as we saw earlier, the system needs to keep, okay? All the other decision variables are more of an additional decision variables or auxiliary decision variables that make it convenient to express the model formulation. Okay, yeah. So I'll highlight a few of the important components of the model. Okay, yeah. So the objective function minimizes the total supply chain cost, which consists of 3 components. Okay, this is a very comprehensive objective function, by the way. The first term captures the so-called cost of goods sold. Okay, these are the costs accumulated through the bill of material for the end products. Okay, like the fresh table grapes, the raisins and the wine. And the second part, you see the square root here. That is the way we capture the safety stock. Okay, the inventory, right? We placed throughout the supply chain. Okay, the third part is a very important part that captures the so-called pipeline inventory, okay, or working process inventory, right, which can be huge if the supply chain has a long, cycle time or lead time. Okay, yeah. So the constraints, the first few set of constraints will make sure every node is assigned with one option. Okay, that's the first constraint. The following 4 constraints computes the corresponding lead time, cost, and loss rate based on the binary decision variable xikt. That's the option selection decision variable. Okay, yeah. And we have other constraints to compute the inbound and outbound service time, right? And the way we make sure the use of resources does not exceed the available capacity of resources. Okay, yeah. Due to the time limitation, I will skip more details about the model formulation, but feel free to get our paper if you are interested in the details. Okay, yeah. The model, again, is a mixed integer nonlinear programming model. The good news is there are commercially available solver we can use, okay, yeah, readily available through GAMS, okay, yeah. And sometimes we can also develop some meta-heuristic algorithm, right, to solve this large-scale MIMP model, like genetic algorithm, yeah, is a good candidate, okay? All right, with a few more minutes left, I will share with you some of the results, okay, of our case study. Yeah, I will highlight the most important findings. So this table compares our optimal solution, okay, yeah, through the optimization model with 2 heuristics, okay. Yeah, heuristics means they are simple, approach to address the same problem. They are simple, but they may not, give a very good solution. So one is called minimum cost. That is, we simply choose the option with the minimum cost, right? This is often, people do when we want to emphasize cost saving, okay? Or, on the other extreme, we want to emphasize quality, right? Food quality. We choose the option with the highest quality, but you can imagine that will potentially make the supply chain very costly, okay? So we compare the optimal solution with these 2 heuristics and under the linear quality function and nonlinear quality function, okay? Yeah. So I want to draw your attention on the last a few rows on the financials, okay? Yeah, so first pay attention to the, the total net profit, right? So you can see the optimal approach would generate the highest profitability, okay, yeah, for the supply chain. And strikingly, when we assume a nonlinear quality function where food quality goes down rapidly, right, with shelf time, so you see this is where the minimum cost heuristic suffers a lot, okay, because that's where you're going to basically lose your food quality that making the end products not sellable, not marketable, okay? The supply chain, the company will actually lose profit, okay? The profit is negative. So so basically it shows a significant need right? An advantage of using the optimization approach, okay, to address this problem. Yeah. And this picture shows you the actual configuration, right? So by these little boxes, we're illustrating where the safety stock should be, right? So you can see, interestingly, for reasons. Now, it's interesting to realize that reasons is relatively non-perishable. See, that's very important, okay? There is actually a good reason why we address raisins and fresh table grapes simultaneously, right? So for raisins, you can see it's more of a make-to-stock configuration. Everybody see that, right? Because we recommend more safety stock for the end products, right? So you can compare with fresh table grape. Actually, we keep less stock for the fresh table grape at the end, but there are some inventory and safety stock spread it out, right? Spread it out the supply chain. Yeah, the wine segment is kind of interesting. Okay, kind of very different, and we see kind of more uniform recommendations or positioning of inventories throughout the supply chain. All right, so here is another table of highlighting the the advantages of using the optimization approach, okay, by looking into other financial metrics, okay, as you can see. Yeah, so what is important here is observing the trade-off, right? You see there's a trade-off of these metrics, okay? For example, the maximum quality heuristic will have a good performance, right? Good performance on the revenue. Everybody see that? Because the quality of the product is good, right? But on the other hand, it suffers a lot on the pipeline stock cost because that's where you presumably gonna keep lots of working process inventory, because the cost of configuring those high the loss reduction technology can be expensive. Okay, yeah. So observing the trade-off of these multiple performance metrics is insightful. All right, very quickly to summarize, we developed a new modeling framework, okay, to address the food supply chain configuration problem. To highlight, this framework should be able to capture the unique characteristics of the food supply chain, which often include perishability issue and food loss and waste. And at the same time, we often want to address the multiple performance metrics, and they are often conflicting with each other. For example, efficiency, quality, and resilience. So moving forward, apparently there are lots of opportunities, right? With this framework, we will be able to, apply or adapt, right? With very, very much possible modification or extension to address different, food products, right? For example, different vegetables, or getting into the meat and poultry industry, right? Yeah, really, really important sector, in the food and ag industry. All right, that's all I have, and I'll be happy to hear your comments and answer any questions you may have.
Thank you very much, Dr. Lee. If there are any questions, please feel free to unmute and ask your question.
I have a question. Professor Lee.
Hi.
Hi.
Hi, Jenda. Yeah.
Yes. Interesting presentation. So I was wondering if your model is pretty genetic, so general, and applicable to many like supply chain problems. So your mathematical model is comprehensive enough to cover most of supply chain issues, right?
Excellent question, Jenna. Thank you. Yes, the underlying modeling framework is quite general. Okay, indeed, the original development of the supply chain configuration modeling framework actually came out to address mostly manufacturing supply chain. Okay, yeah, there are some earlier references about the original supply chain configuration problem I can share, but most of the existing work address the PC supply chain, for example, in a manufacturing setting. So our work, we were able to extend that framework, right, to address food and agriculture by building in these features to capture the unique characteristics in the food supply chain, such as perishability and food loss and waste. But in general, yeah, you are right. This modeling framework can be applied for different variety of food products. Okay, yeah. So far, we've been focusing on grape supply chain. That's where we did quite a lot on studies so far, but there are significant opportunities to address, for example, rice supply chain. Right. So another project I'm working with my colleagues in is on addressing a rice supply chain, right? And there are certainly opportunity to dig into the vegetable side, right? And like I mentioned, the meat and poultry sector is very, very important. Actually, there are lots of issues there because, for example, we could address the use of new technology, right, such as sensors, right, at different stage of a poultry supply chain to improve food quality. But guess what? The use of those sensors can be expensive, right? So our interest would be, how do we configure a meat supply chain, right, with the use of new technology, in the most economic way?
So did you also take into account, there's tons of information about geospatial distribution system. And if you take into account those kind of information, it seems to me your optimization will be much better.
That's a very good point. So there are significant opportunities there as well. Okay, so a related modeling framework is to address the strategic network design. That's where we can directly address the geographic location of different facilities, warehouses, processing facilities, for example. So in this modeling framework, our focus is on the more tactical level. So you can see the framework address the bill of materials. So that's a slightly different approach to addressing supply chain. But I agree with you, they are closely related. Yeah. Lots of opportunities to incorporate the GIS information. And related to that, Jenna, I think I'd also like to mention the opportunities of using more climate data. Right. Yeah. I mean, there are tremendous opportunities there. Yeah, I believe.
No one else has a question, so I can ask you another informal question.
Yeah.
Okay. So I know there's a few folks from your campus working with SLU related to geospatial, and are you aware of that?
I'm aware of that. I think we have a somewhat sort of a consortium with the NGA here. Right? They have a big operation here in St. Louis, and I know AMSO also have some representatives from the NGA, some program going on, and certainly collaboration with SLU. Yeah, I'm aware of that.
Okay.
Yes.
Well, the reason I ask is because I'm also actively involved in that group because we are okay. a university consortium.
Yeah. So I'd love to get connected. If you see the good relevance and good synergies there, yeah, absolutely. Our department actually participated in a new GIS undergraduate certificate, I think, or minor program in data science. We are trying to launch. One of our faculty developed a course on using, data visualization, including ArcGIS for, business applications. So that's certainly an area, I'm very interested. Yeah.
Thank you.
Thanks.
Any other questions for Dr. Lee?
So, Haitao, you never been visiting our campus yet, even, right? Even we are so close.
I paid a couple of visits.
Okay.
So we have some good relationship actually with your engineering management program.
Who you visit? Is it
Yes,
Susie?
with Susie. I
She
know
left
Susie
already, you know that.
recently left. Yeah,
She
I know
left us.
Susie left. Yeah,
Right.
but I'd love to visit your team. Yeah, Jenna, absolutely. At some point, it's pretty close, like you said. Why not?
Well, if you look at the mathematical framework, we use a similar framework for other purpose.
Yeah.
It's basically genetic algorithm and other optimization, multi-objective optimization, basically.
Yep.
So we use that a lot for infrastructure as well. So.
Yeah. So absolutely, I do see lots of synergies we have. So I'd love to visit you and your team at some point, and maybe invite you.
Yeah,
to our department. Yeah, I'd love to do that as well.
Yeah, if the pandemic is cleaned up further, that would be good. We can visit in person. Because right now it's still pretty dangerous. You know that, right? A couple of my colleagues and students got affected from one conference. 100%, everyone got infected from a conference. So it's a very, very risky still.
Okay.
Dr. Lee, I do have a question on the presentation.
Go ahead.
So what would be the effect of, let's say, port delays on the model that you have? So we've had significant delays at various ports, and if material is coming from the supply side and that needs to use the port, how would the model adjust that?
Yes, excellent question, Amal. So the model is able to be applied to address that. Okay, the best way for me to show you is, let me share my screen again. So you see several rows at the bottom, okay? This is where we consider transportation mode.
I see.
Are you able to see that? Yeah.
Right.
You see
Yes.
train and truck. So, and ocean, right? So this is where what we can do is, capture the cost and lead time of that transportation mode.
I see.
Yeah. So it's certainly possible. But I would say there is also opportunity to, if we want to, really get into the details, right? The complexity of addressing the overseas transport, in this problem context, we may also think about some new modeling features, right? But even with the current modeling framework, we can somehow, capture that that issue, in a relatively easy way. Yeah.
Okay, and I would imagine it would have to be somewhat dynamic because the conditions on the ports would change depending on availability of workers and so on and so forth. So
that's a very good point, Amal. There is actually, so you are right. The current model we presented here is more of a static model.
Right.
Okay. Yeah. It's like a one shot. So typically, through this configuration problem, the company typically look at the configuration in the next 6 months to a year, I would say, kind of the tactical level, okay? But you are right. Nowadays we are looking at, lots of dynamics, the environment changing very quickly. And if the company or farms has the flexibility, right, to change these options in a more frequent way, right? So we could address a more dynamic supply chain configuration. Actually, I have not seen much modeling framework on that. I do know there's one paper coming out, several years ago, but the model, yeah, the model they presented, in my opinion, was not very elegant. So if we want, we might. I do see opportunity to come up with some more elegant way to capture the dynamics of supply chain configuration. Yeah, but that's a very good point, Amal. Thanks.
Thank you. Any other questions or comments? Well, thank you very much, Dr. Lee. We really appreciate your time and the presentation. Thank you so much.
Thank you. It's my pleasure. Thank you all for joining.
All right. We'll end the presentation here, and then for the students in the class, I'll communicate what we'll have next week. Thank you.
Thanks all.